Hey, Ken.
Hello, sorry I'm late.
I was almost wondering no one would be there. Gianni said he's not feeling well, so he won't be attending.
Okay.
And Abhiyan said apparently he needs to have a COVID test.
Oh, wow.
So Abhiyan shares the office, so he wanted to be safe. So
Okay.
he's also.
All right. Sounds good.
But I was expecting them to be online, but probably they did not realize that that option is there.
Yeah, I could have probably forgotten about it since it's been so long.
Yeah.
Probably just thought about the recording too.
Yeah, exactly. Yeah. You have homework. And it's due. It's due on Thursday. And there'll be one more homework. Probably. Should be more careful with the camera so that you don't miss it. Yeah. Okay, so we were trying to do the expressions for radiation in the frequency domain. We did the time domain, and we would like to do that in the frequency domain. And the idea is there was this nice prescription that wherever you see a derivative, replace it with frequency. That's the point. So this is radiation. It's good to say spectral distribution of radiation. Spectral distribution of radiation. And we showed that, remember, we have negative del square plus 1 over c square partial derivative square of phi, right? That's our wave equation. And a new suitable way to go into Fourier space is to replace all the derivatives with minus I omega. You feel, and immediately say that we are working in the frequency domain. And in that manner, our equation becomes derivative becomes there is a minus omega square over c square. Now we are in frequency domain. That's equal to 1 over epsilon naught times rho. This is in the time domain. So that's an immediate way of going from one to the other. The same equations for the magnetic potential is omega mu naught times J omega. The Green's function associated with this then can be written as Green's function, this time in frequency space. That's Q R minus R prime. And G is equal to here, I think I might be able to accommodate this here. So this is G R minus R prime. Squeeze. So we have the static scenario immediately there. It is I omega times R minus R prime over C. So we check our time. Okay. Okay. This is the total Green's function in the radiation or in the far field approximation. So that's far field. So this is far field approximation. That means to say that all the R prime, this is very much small compared to R. As a length, this is really small. And in that case, this takes the form. We have e raised to IKR over 4 pi R. So this becomes just R, that becomes omega C over R, and that is exponential of minus I K divided with R prime. So that's a neat feature. So that's uses the approximation that R minus R prime is equal to, is approximately equal to R minus R hat divided with R prime. And that's far field approximation. And here we have assumed K, so the notation here is that K is equal to omega over C and R hat. So a diagram helps here. So notice, so this is a region where R prime is. So that's your R prime. R is somewhere here. This it's very far away, and K is in the direction of R, except its length is omega over C. With this feature, we can put this back in And this piece here makes sure that it is only the Fourier transform that contributes very nicely. This becomes the phi or omega, which we wrote this last time. This is equal to 1 e raised to I k r over r times 1 over 4 pi epsilon naught. Right. And just Fourier transform source. So this is Fourier transform in the sense now this is k omega. This k has an angular dependence in it in the sense that it depends on r hat. So that's angle dependent, but otherwise it depends only on the frequency, right? It's on the dome. That's what you say. It's only in the limit r tends to infinity contributes. All the r dependence is in this piece here, the linear dependence, and there is only frequency dependence on the part. Yes.
The R prime is pointing to our like radiation source, right?
Yes, this points in the direction of the source.
Okay.
Yes,
Okay.
correct. So if there is this is the antenna, and this is some arbitrary origin, which is typically inside of the source itself. But if you have only single source, it doesn't really matter. You can choose that as origin. But if you have 2 points in the source, one of them is the origin, the other one is R prime.
Okay.
Like if there are 3 points in the source, then one is the origin, rest matters. And that's where that interference term comes in. R minus R prime is here. So there's a slight extra length that you go, and that can interfere with on the other side. That's the idea. And we have approximated it, but we are still able to capture that interference or interference contribution there, and it does contribute. And in the leading order, it does contribute. That's a point. Good question. Yes. Okay. Same thing for A. Notice this is all algebraic, so it is kind of in the frequency domain. It becomes very simple. The Fourier transform of the current density is pretty much just multiplying it by some factors gives you your electric potential, and the same thing for the magnetic potential. Remember, if you're in the time domain, you have to do the integral, and there is a little more work to be done. Okay, so that's your electric and magnetic potential. We are interested in the electric field typically. Electric field or omega in the frequency space would be. Let me. This is typically like this, right? So it's minus gradient of phi RT minus d by dt of A RT. And magnetic field is across. We are interested in the frequency pieces. We would like to go from t to omega, and accordingly d by dt has to go to omega. And we also did last time that when we are doing gradient, it is sufficient to just replace gradient with IK. So this is in the far field. So in the far field approximation. So in the far field approximation, wherever you see a gradient, you can replace it with IK. And K, remember, is omega over C times R hat. That's not always, like in Fourier transform that works, but this is not really a Fourier transform in position, right? This is a gradient. You still have R dependence in this, but in the far field regime, this is nothing but omega over C times R hat. Right? So that we did last time we showed that that works. Now with that, we can proceed to calculate our fields. Let me, what's the spot? Okay. So magnetic field then, we should move. Magnetic field then is our omega is simply gradient gets replaced with I, okay, at crossed with A. Let me write this as I have a K which is I times omega over C times R hat crossed with A is equal to exponential I K R over R times mu naught over 4 pi times J. It will be convenient to write this as C times B or omega is equal to, I'll put a minus sign in here, at crossed with e raised to IKR. Let me start with, I multiplied by a C so that I accommodated here, mu naught C over 4 pi. That's that resistance, diamond has a dimension of resistance. And then I have e raised to IKR over R. And there is an I omega over C, which is acts like a derivative, right? Always think that it is a derivative of velocity that contributes. It's an acceleration that contributes to radiation. Current is like velocity, and omega is like a derivative. So that's the acceleration, so derivative of this. So let's write that together. And that's minus I omega over C. This should be in your mind, you want to keep this as derivative times J. Remember, minus I omega is derivative time. So write that like that so that it is d by dt of J. That's what you keep in mind. So acceleration times, this is the far field approximation Green's function times R crossed with that. So this is the source and often you in the time domain also we had an R crossed with some quantity that shows up. So this is the property of the source, and R crossed with that gives you the magnetic field in the far field region. Is that clear? Any questions? Okay. We would like magnetic field also to come out like that, but electric field has two pieces. So electric field R omega is equal to minus IK hat times phi of R omega, and you have a plus I omega times A R omega. Put this, put the Green's function in there. Let's simplify, or let's explicitly write the terms. So this is minus I omega over C times R hat times phi is e raised to ikr over r 1 over 4 pi epsilon naught times rho of k omega. Same thing for A, and A is e raised to ikr r mu naught over 4 pi times j. There. This is the same as pull things out. Let's say I bring out an I omega over C, let's say. Yeah, I omega e raised to ikr over r mu naught over 4 pi. That's this whole piece that's come out. And what is remaining is there is a ikr, c, the minus 1 over c, 1 over epsilon naught, mu naught, and that is a rho of k omega. And there's a r hat, I suppose. Okay, better. C times epsilon naught mu naught is nothing but C itself, so I can write that upstairs. Maybe pull out that negative sign. One more thing, so this is minus I omega over C e raised to ikr mu naught C over 4 pi, and r hat times C times rho k omega minus of j. Seems like that's all we can have, but there is a connection between rho and j. Let's analyze that for a minute. Let's digress a little bit. So remember that charge conservation requires d by dt of rho comma t is plus divergence of j of t is equal to 0, right? That's the statement of conservation of charge. Fourier transform this immediately uses minus I omega, and Fourier transform both in position and time. So this is k omega plus I times k with j k omega. Is that clear? So I simply replace derivatives with omega gradient with I times k. This can be read off as rewrite. This I cancels out, right? Let's put it as so I omega rho of k omega is equal to I omega over c times r hat with j of k omega. I omega cancels out, so we have c times rho is nothing but r hat times j of k omega. So current conservation or charge conservation in the frequency domain, especially with the replacement of K with omega over C reads like this. In the far field approximation, it reads like that. And that would mean that what we have there in the expression for the electric field is R hat times K omega minus of J K omega is equal to, replace this, so it is R hat times R hat dotted with J minus of J of K omega, which if I suppress K omega for a minute, that's R hat dotted with J minus of R hat dotted with R hat times J. And that should remind us of an identity in vector product. That's nothing but double cross product, right? So this is hat crossed with J. So it's R hat and then it's J. If I go back to the expression for the electric field now, that means that I can replace this quantity. So it's electric field. So I can replace this quantity C rho minus J with the double cross product. So that's equal to the electric field is equal to minus I omega over C e raised to I K R over R naught C over 4 pi times R hat crossed with R hat crossed with J with K omega. But if you notice the expression for the magnetic field above, I can rewrite this. I can collect these terms here exactly in that form, right? So this is I should put it here. And I learned that this is equal to put all this right, so that the minus I omega over C e raised to I K R mu naught over C. Put all that in here as an R hat, but I need a negative sign in there, so supply a negative R hat. So this is nothing but negative R hat crossed with magnetic field C times B or omega. It is very convenient. So what we have is there is an antenna. Think of an antenna which is a current. It's a Fourier transform of the current. Notice no integrals here. The moment you have the Fourier transform, you know what's going to be the magnetic field at the dome at a very far field region. This is the R dependence. That's the only R dependence here. This only depends on the orientation of the observer, where exactly you're observing. And this whole thing is a source dependent quantity. And you have magnetic field given by that. And once you know the magnetic field, uh, cross it with the r hat vector, and you get the magnetic field. Is that clear? And we did this in the time domain, but now we have the whole thing in the Fourier frequency space too. Any questions? Okay, so that's good. We have the fields now, but typically when we say spectral distribution, we would like to know how much is the power radiated. It's how much energy is going into a particular solid angle. That's of more interest. So let's go back and try that. So we would remember we have derivative of u with respect to time. This is all in time domain plus divergence of the Poynting vector plus j dotted with e is equal to 0. We are interested in this piece where S now is E cross with D over mu naught. That's your Poynting vector. Let's take this piece. This piece tells us how much energy is, that's a flux of energy being thrown into the dome region. And that's equals to, let's write that as dE by dt. That's the energy rate. So this is now the total energy, right? Integrated out. So this is equal to integrate over the whole volume dotted with S. Where S now, write that in a minute. But everything is in time. This is now the total energy. Notice that's not U, that's the total energy, and on the flux of that, or you can say this is the power, right? Power radiated over the whole dome is this volume integral. Use divergence theorem, and we get this is a closed volume. So that's dA dotted with S or T. This is our hat, so that's the area. So that's your hat dotted with S. dA can be written as d omega, that's a solid angle, times r square. We did that when we were doing the time domain also. And in that way, we can say that the energy radiated per unit time, per unit solid angle is equal to r square times r hat dotted with the Poynting vector, which is E cross. So everything is in R position and time now. E or comma T over mu naught. Right, so let me write the mu naught here. Replace the cross and R cross E is nothing but magnetic field. R cross E is C times B. So this is equal to R square times mu naught times C times B or P dotted with D or comma P. Supply a C there and a C here. So it's R square times magnetic field square. So that's a relation we found earlier, but now we are interested in the frequency domain. This is all in time, so integrate this out. So how much energy is radiated in a single solid angle over the total time will be equal to R square over mu naught times C minus infinity to plus infinity dt times C T or T dotted with C T. Clear? I'm interested in the frequency domain, but now the point is to Fourier transform at this stage. Whenever we have double functions with 2 times in it, it is best to integrate over time and then we get the frequency. So that's a trick here and you do this. So now let's do the Fourier transform and you have to Fourier transform this, you have to Fourier transform that, and the time integral will kill the Fourier transform and it will suddenly become in the frequency domain. So let's, and since it's a standard trick, let me do that on a separate board space. So this is, let's take any, let me take any function. It doesn't have to be a magnetic field. So this is f of t, and let's say f of t. Can I write g of? Yeah, I can write g of t. I have 2 functions whose both are dependent on time, and now the total time integral would be equal to t. Fourier transform both. Fourier transform the first one, so it's d omega over d omega prime. This is minus I omega prime t times f tilde of omega prime. Fourier transform, I have not been writing that tilde, but here just temporarily. That's the first Fourier transform, and the second Fourier transform is d omega double prime over 2 pi minus I omega double prime t times g tilde. That's equal to move the time integral in, the omegas out, d omega prime over 2 pi double prime over 2 pi f tilde omega prime g tilde double prime and dt and e raised to time, that is a minus I t, and that is omega prime plus omega prime. Is that clear? And what is the time integral equal to? There's nothing in there, that's just an exponential integral. It's clear that when when omega prime plus omega prime is 0, that's infinity. Otherwise, it's an oscillatory integral. It can be argued that it is 0. So that's a delta function. So this whole thing is a delta function. That's equal to plus d omega prime over 2 pi prime over 2 pi omega prime g tilde omega double prime, and that's 2 pi times delta function of omega prime plus omega double prime. So I can replace the omega double prime with minus omega prime, complete the omega prime integral, so it's minus infinity plus infinity prime 2 pi tilde of minus omega prime. Yes.
How did you catch that that was a delta function?
If this is slightly tricky here, what you have to first do is that you have to take this into a finite domain, take the limit minus L to plus L. But even before that, you can argue that if this was 0, this is a function of only omega. If this was 0, exponential goes away, and that's infinity. But if it is not 0, exponentials are cosine and sines. So they're oscillatory, so they're 0. That argument is tricky because it's an infinite region, so you have to break it into wavelengths.
I see.
But the simple argument is that this is oscillatory, so that's 0. One case it is 0, one case it's infinity, and the total is equal to 1, so it satisfies the conditions for a delta function. So that's a simple way of looking at it.
And then there's 2 pi. Where does that come from?
2 pi, because you want to show that, so if this was a delta function, so you have to show that so let's say this is dt times e raised to minus it omega, that's it. Okay. So that's what we are arguing, right? Let's say this is f of omega. That's what we are trying to say is a delta function. If it is really a delta function, I should be able to do minus infinity to plus infinity. The omega of f of omega should be equal to 1, right? So this is equal to, and will I get it? So let's see. So this is minus infinity to plus infinity. The omega times dt e raised to minus it omega. Not like this, not like this. Let's see how this comes. You can say this is the definition of a Fourier transform, correct? Yeah, think of this like this. Yeah, think of it as a Fourier transform. If this is taken as a Fourier transform, think of this as 1, right? And this is nothing but f tilde of t. So the Fourier transform of f of omega is actually 1.
Yeah, right.
Fourier transform this means that f tilde of t, which is equal to 1, right? Because it's 1. Now use the definition of Fourier transform, that's minus infinity to plus infinity d omega over 2 pi times exponential of it omega. And you see this 2 pi coming up, right? This times this is equal to 2 pi. So that's the so you can say for the consistency of the Fourier transform, you need to have.
Thank you.
Okay. So yeah, what we have shown then is that the total integral of two functions, product of two functions in time space, is the same as the frequency integral in the frequency space, right? Just that it has to be done with minus omega, and that also means that this is star. So it is good to note that G of I mean, in the Fourier space, this is the same as omega star, complex conjugate, because Fourier space allows things to be complex, even though the real in the time domain things could be real. In the time Fourier space things could be complex. Using that, we have in the energy radiated in the per solid angle is nothing but R square over mu naught C. Switch over to frequency domain, and that's z minus infinity to plus infinity, the omega over 2 pi, and this is C times B. Now, just since these are the two same quantities, we'll have F times F star. That's complex conjugate. So if we are talking about the magnitude of that conjugate. Is that the place? Frequency, usually things are even functions of frequency. So write this as 0 to infinity and make that 2 times that, and talk about per frequency, right? So we want to talk about how much energy is pushed into a solid angle per unit frequency. That's the spectral distribution. So d omega comes down, and we have 1 over pi times r square over mu naught times c times the magnetic field, or omega. So once I know the magnetic field, the squared quantity of that in the spectral or the spectral dependence of the magnetic field decides how much energy is going into a particular solid angle per unit color, per unit spectral distribution is per unit color. So put that in. We have the expression for magnetic field. Let's put this in and see what it is. Magnetic field is down here, right? So this is R crossed with J. All these expressions. Questions? Okay. Okay, substitute that is in that. So we have energy per unit frequency per unit solid angle. That's equal to 1 over pi times r square over mu naught times c. And this is squared quantity, so there is an r cross j for sure. So this is mu naught c over 4 pi whole square. This is a magnitude square, so this is e raised to ikr. Magnitude square, that's 1 divided by r square. and I goes away, omega square over c square. And there is a r hat crossed with j. Square. R square cancels out. Exponential like r is 1. There is a 4 pi square, I suppose. Let's see how I want to write this. So I think that's reasonable to write this as I take a 4 pi from here, 1 over 4 pi square. And mu naught c over 4 pi. This is that is good to keep it separately. Then omega square over c square and or hat crossed with j. So that serves as an energy per unit solid angle per frequency. Yes.
We have like the I omega. Does the I square?
I square is -1, right?
Right.
And it's a magnitude.
So it just gets.
Yeah, so it is minus I. So this is minus I times the complex conjugate of this, this plus I, right? So minus of, so this is plus
Right,
1.
right.
Right. So that will always go away. Exponential is 1, right, under the complex conjugation. Yeah. And I think c squared, yeah, it's okay. Yeah, okay. So I think I get correct, I suppose. Epsilon naught. I think so. Because I have this expression whether this epsilon or not. Give me a second. Am I missing a C by any chance?
I didn't see.
I think it's okay, right? May not C. I think it's okay. Yes. Oh, here, yeah, it matters. Okay, good. Okay. Sometimes this is just, I think later, I think in the next lecture, I'll be doing Cherenkov radiation. It is also good to point out. So this is a good, this is the relation that will be most useful when you're working with antenna, right? Antenna is decided by the current density, how much current is going through the wire gives you the Fourier transform immediately, and put this in, almost immediately you get that. So the only thing to do is the Fourier transform. But sometimes we are interested in or in Cherenkov radiation. It is good to observe that this is a cross product, and notice that A cross R hat crossed with J. Right, this is squared, so this is nothing but R hat crossed with J star. Right, that's the 2 and dot, right? And A cross B dotted with A cross B is also equal to R hat. So you go this to this, R hat dotted with R hat times J hat, J dotted with J star, and do the cross. So it is minus of R hat dotted with J and R hat dotted with J star. That's a vector relation. If you want, R hat dotted with R hat is 1, so this is nothing but the magnitude of J K omega square, and this is a magnitude of R hat dotted with J of K omega. But we just now earlier in the lecture showed that using current conservation, or sorry, using charge conservation, we know that R hat dotted with J was nothing but C times rho. So this is nothing but so this is J K omega square minus of C square times rho. So in this way, we write it in terms of both current and charge dependence. So in this manner, you can say energy per unit solid angle per unit frequency is equal to 1 over 4 pi squared times V naught C over 4 pi times do I want to write omega inside? No. It's just omega square over C square times so that will be an expression that will be useful when we are working on Cherenkov radiation. Question, yeah.
The top left equation there, governing the energy of the system. Yes, yeah. So I'm kind of losing sight of why why is it useful to us?
Oh, means like why I started from this. Okay, so the point is, so the question is, why did we begin from here?
Yeah, like why are we like we already have the electric field and the magnetic field and the subsequent parts of it in Fourier, like in frequency form.
Correct.
So now we are using the time domain energy equation there. Like what is the benefit of it to get the electric field and magnetic field in terms of energy?
The point is this term here is telling me how much, what is the flux of energy crossing through that door in the time domain, right? And I don't know what it is, what does it look like in the Fourier domain. Right? I would like to want to talk about how much energy per frequency is going in there, not as a time. So I want to convert this equation. This is the conservation of energy equation in the time domain, which is usually written in time domain. I would like to write it in the frequency domain. And I'm interested only in this term because I'm interested only in the flux. I don't care about how much energy is, like some of the energy might be used up in a charge, for example. I don't really mind that. I'm only interested in how much is crossing that value. Is that clear? Or maybe,
yes.
maybe I was not.
I guess like, but in so by knowing the amount of flux that crosses the dome, how is that useful if we've already found the electric field at that? The magnetic
Because S,
field?
maybe the point is S is this. The flux of energy is decided by E and B. E cross B, like it is like saying, think of electromagnetic wave, right? That's your electromagnetic wave, correct?
Mhm.
So this is E, that's B, and that's your K. That's how much energy is going in this direction, in the wave, right? And it is given by E crossed with B. Right? So I have a B here, I have an E, and I also know that the cross of that will be in the direction of R hat. I know that also. But all this is in the time domain. I want to switch that into frequency domain. So mainly to get all these factors, like actually the 1/pi, it is very clear that it will be in the K direction. It will be the square of the magnetic field. That's not a confusion. It is mostly for the factors we are doing to get a more precise expression. Did I answer? I'm not sure if I completely captured the question.
I guess I'm just like thinking of it in terms of like why it's very important to know. Like what would be the next step of like, so you found the energy flux, like how would you utilize that in some like physically?
Oh, physical. So for example, yeah. So for example, if you're constructing an antenna, you would like to know what intensity. So I'm, let's say wattage, right? You're spending 5 watts of energy or power into your circuit, into your antenna. You would like to know how much of that power went in the X direction, east direction, how much went into the north direction, and how much went into the vertical direction.
I see.
This is the distribution. How much energy went into this solid angle? Out of that, how much red color went into them? How much blue color went into them? Right? Not all the colors go everywhere. There is a distribution there. Right? That depends on you. You can change, you can design your antenna oscillation in such a way that everything goes in one particular direction. So you can control it. Right? So that's a distribution. That's
cool.
Okay.
Awesome.
That's the idea.
Okay, cool.
So it is energy per unit solid angle, energy per unit frequency, per unit color, per unit angle.
Right. Thank you.
And yeah, like earlier we were talking about time dependence, like as a time function of time, how much is it? But typically it is a frequency that is of more interest in a practical.
Yes.
Okay, so in the last 10 minutes, let me give you some help with the homework. So in the homework, what you do is, so this is general expression, right? Or any J. In your homework, you say that this is actually a specific antenna. So an example would be, so that's your homework. This is a loop antenna. Loop antenna means that you have just a current that is going in a loop. What will its current? We first write what is its current in J of R and time. So as a function of R and and this is current per unit area. So what is its direction? It is, let's say this is z equal to 0. This is in the xy plane. So this is equal to phi hat direction. It's a tangent to a circle in the polar coordinates. It's phi hat. And it is also good to, at this point itself, write this as r prime and p prime so that you don't confuse with your observer point and the source point. So these are all going to be sources. So this is phi prime. Okay? And that is a current. So that's current, which could be any function of time. We would say it is as a sine function actually. And now, where is this current sitting? It is in the z equal to 0 plane. So z prime minus 0 plane. I get z prime is equal to 0. That's an xy plane. And it is also surviving only at the radius a. So let's say this is a circle of radius a. So this is rho prime minus a. Rho prime is the cylindrical radius. That's fine. Current density. If I want to use this in this expression, I should be able to do the Fourier transform of this. And let's try to do that. Let's give you sufficient steps there. Because once you have that, you have the energy per unit solid angle immediately.
You said this was the z plane that we're looking at.
Yeah, so this is the xy plane.
Right.
So this is x prime, y prime plane. So z prime is 0. That's z prime equal to 0, right? So I chose that.
So understood.
Fourier transform of that would be g of k omega would be d cube r prime et prime minus infinity to plus infinity is I k dotted with r prime e raised to I, this is minus, and I omega times t prime and j of rt. Remember that phi prime changes from point to point, so it cannot actually come out of the integral. Put in everything in here. So this is minus infinity to plus infinity. Let's work in cylindrical coordinates. So it's rho prime, d rho prime, d phi prime, 0 to 2 pi, and that is z prime minus plus infinity, and that is dt prime. This is k dotted with r, that's a 3-dimensional quantity. So write that as minus I k per now. This k has 3 directions, right? K, remember, is r hat. I can write that as r hat per I omega over c. R hat per means in the xy plane. R hat per is xy plane, which is rho hat. So this is rho hat dotted with rho prime, and that is the z direction, so it's minus I omega over c times z prime. Is that an easier way of doing this? Is c hat and c hat, yeah, so this is c z prime cosine theta. And then there is e raised to I omega t prime. This is I of t prime delta of rho prime minus a, and this is delta of z prime. Yeah, I think so.
And this z prime cosine theta is from your r hat dot r.
Correct. R hat or z hat dotted with
Oh, right. Because
z.
k.
Yeah. But it doesn't matter because that is going to go to zero anyway. Z prime is zero, right? And R prime, rho prime can set to be equal to A. So these two integrals can be done. So let's say, so what's happening? And there was a phi hat also, right? Phi prime. Phi prime hat is also.
Sorry. You have two different k vectors, right? Is that what?
Where what happened?
So you have one k vector for z and one for the row. Is that how we have the row hat?
Yeah. So what I did was k. So k is actually omega over c times r hat, right? R hat is nothing but omega over c times let's say x what should I put it? Let's call this R hat is that okay to say? Oh, I'm saying this. I want to remove, okay, this is x I hat plus y j hat plus z k hat, right? Divided by x squared plus y squared plus z squared. Agreed?
Yes.
That's surely the case. Now I'm interested in this piece here. So this is omega over c. This is rho hat for me. And what happens to the z then? Is that
You just separate it? Yeah. You're saying like the row hat is the angle on the xy plane.
huh?
Are you saying that the row hat is the like fixed angle for the xy plane?
Give me a second. Maybe I don't want to write it like that. Yeah, just let me say, let me say that, this is surely this way, right? X I hat times y j hat times the square root y square plus z hat plus z over square root over k hat, right? Is that clear?
Mm-hmm.
And this one went in here. And this one goes in here. So R hat I'm splitting. Hold on. Maybe I can write it this way. K dotted with vector R prime is equal to K dotted with, this has a rho direction in it plus a z direction in it, right? So z prime times k hat, z hat. Is that clear? This I since this is going to contribute only the curve in this, so this I call it K curve. This direction, dotted with rho prime. And the other one I simply call KZ times Z prime. And that's in the Z direction. Is that clear?
Mhm.
So this is the language here that, I mean, I'm breaking the K in the direction of rho. Does that help?
So rho is
So it is not K, it is not K, it is K curve. It is a component of K in the perpendicular plane, if you want.
rho isn't like the charge.
Rho is into, that's the confusion. Oh, no, this is, rho is the radial, like
Like our omega.
let me say this. We have X, Y, Z, right? Coordinates in cylindrical coordinate will become rho, phi, and Z. So it is the cylindrical coordinate of radius.
Thank you.
Yes. Okay. Yeah, we use the same thing for the charge density also. But yeah.
Thank
you. Okay. So in that sense, that's what the K curve is. And let me write that as K curve then. This K curve. Got it. Oops. And there is a phi prime fact also. Z prime integral goes away. T prime integral just gives me I of omega. So I of omega comes out. That's a Fourier transform of I, this boxed quantity and this integral, and my omega t. So three boxed quantities are can be separated out immediately. The Z prime integral has these arrows coming in. That's just one, because delta function just makes that one. And what I'm remaining is your A. So that's the rho prime gets replaced with A. So you have 0 to 2 pi E phi prime times exponential of minus I K curve dotted with rho prime, but this is rho prime has to be set to A times phi prime with rho prime set to A. It's like saying you're adding up all your phi prime angle along a circle, but this is dotted in K prime is a vector which will have some angle associated with it. So this is equal to I omega 0 to pi E phi prime and exponential of that will have its own angle. So this is minus I K curve. Rho prime is A now, right? Because rho prime is set to A. And the angle between these two vectors is cosine of some angle phi, which decides your K, and phi prime. And phi prime itself as a vector is minus sine of phi prime, the I direction, plus cosine of phi prime in the J direction. Since I'm way past, it's already 5 minutes crossed, I will just give a hint here. This integral, here, after you expand this out, you do phi minus phi prime has to be substituted as phi double prime, and write this integral in the direction of rho hat and phi hat. There will be two integrals. And this integral will be 0. Show that this will be 0. And we will be able to show that j of k omega is equal to I of omega. Now in the phi hat direction, in the observer phi hat direction, not the prime, not the source phi hat, but the observer phi hat. And the remaining integral 0 to 2 pi d phi prime times exponential of I k per a times, I think it will be just cosine of phi prime. This is nothing but Bessel function. Probably there will be a cosine, so there will be some function k cosine of this. Check this, and this will be a Bessel function. And once you have that, then you can complete then it's a question of analysis from that. So I give you reasonable number of steps, and these are actually the problem described. But once I tell you, hopefully it's slightly better.
Bessel functions are like for catenary, right? Is it might be
Catenaries are Bessel functions? No, right? Those are no. Bessel functions is when you have this drum, right? Bessel functions are circular functions. So when you have a drum, you have these vibrations, right? The modes of the vibrations are given by Bessel functions.
Okay.
If you have a string, you have sine and cosines, right? In a guitar, when you play your music, the modes are given by the sine and cosine trigonometric function. But if you are on a circular drum and you ask how does it vibrate, what are its modes, then they're Bessel.
Interesting. I thought we maybe applied them to like power lines, like with different.
Those
lengths.
are catenites.
Yeah, I don't.
Yeah, that's
Maybe
I don't think they're, at least not sure. Yeah, I think they're that's a catenary, right? That's the name of that function.
Okay, yeah.
Not sure if that's a Bessel function.
I'll look more into it.
Yeah. Okay, good point. Yeah.
Thank you.
Okay. Hopefully Johnny and Fabian can catch up.